if I do?
Here. First thing I would do is I would rewrite the function. Since we know this root means we've got an x to the 1/2, if we're taking a derivative right now, we've got a quotient. If you want to bring that up, we could make it a product. It really doesn't matter. I'm going to go ahead and bring it up and make it a product. So notice I'm writing the original function. So I haven't taken the derivative yet. There's no f prime. I'm bringing that square root of x up. So I've got the natural log of x multiplied to, it'd be x to the negative 1/2 since we bring that up. Now let's take the derivative. Taking the derivative with a product, you start with the derivative of the first piece. Hopefully we've done enough of these now where you take the derivative of the natural log of x. You appreciate that that's 1 over x. We're multiplying that to this x to the negative 1/2. Adding on, first part, natural log of x, times derivative of the second. So second, we bring down the negative 1/2. You've got x. Subtract 1 away from the power. New power is negative 3/2. There's your product rule in effect. We know now with the further application, having to find these critical numbers, we got to clean this up. As we clean it up with all the negative exponents, make sure you're taking note of how these negative exponents are grouped. I've got a negative exponent grouped with this 1 over x. I've got a negative exponent group with all this stuff here. Those are separate ideas, so I should treat them as separate fractions for the time being. If I set up new fractions down here, in the first fraction, we have a denominator of x times, I'm bringing down that x to the negative 1/2, so it's x to the 1/2 down here. All that would remain as I clean up that first fraction is a 1. All that remains in the numerator, right? For the second fraction, let's see, we have a denominator of 2 from that 1/2 fraction. We have an x to the 3/2 we want to bring to the basement. As far as what's contained now on top, well, you have a natural log of x, and you've got a negative 1, right? So we could make that a negative natural log of x. It's all multiplied anyway. Eventually, you want to put this all together as one fraction, right? So let's take note of a few things. First thing I notice, in this denominator, we've got a couple of x's that are multiplied. So if I add their exponents, I'm going to get an x to the, it'd be 1 1/2, right? So 3/2. Here's what I'm going to do. If this is going to become an x to the 3/2, I'm going to cross this guy out and make that x to the 3/2. Well, now for your common denominator, we've got an x to the 3/2 over here, x to the 3/2 here. All we need to attach to that first fraction is a 2. Right? Attach that to the top and the bottom. That means your simplified derivative, since we now have a common denominator, is going to be 2 from the first fraction's numerator, basically minus, since we're adding the negative here, the natural log of x from the second fraction's numerator, all over common denominator of 2x to the 3/2. All right, so we've got our critical numbers set up to solve for. Probably the does not exist side would be easier at this point. That'd be pretty quick. X should just be 0, right? To reach back a little bit to solve the numerator side, the equal 0 side, because with a logarithm, we got to get the logarithm by itself. So isolate the negative natural log of x. We're subtracting the 2 over. Got negatives on each side, so that's all positive now, if we divide that out. Once you've isolated the logarithm, remember you look at the base of the logarithm, which in this case is e, and you rewrite this in an exponential form. So we write our little merry-go-round here. It's e to the second equals x, and since you're solving for x, there you go. It's e to the second. So our critical numbers, if that's all we were asked to find, our critical numbers would be 0 and e to the second. However, remember what we've talked about with critical numbers in the past? To know that they actually work, you take these numbers, you plug back into the original function, see if you get a real result. You should notice there is an issue right here with 0 if you plug back into the original function. For our purposes, though, with all this increasing, decreasing stuff, it's actually useful to keep that number in here. As a critical number goes, though, it wouldn't be a critical number. So go to your chart now. Just like we did on the previous problem, you've got your x column, you've got your derivative column, you've got your original function, and we are taking the extrema out because we don't have to find them. If we set up our intervals like we did before, we're starting at negative infinity, we're going up to 0, we're pausing at 0, we're going from 0 to e squared, pausing at e squared, and then there's no more critical numbers, so we travel on to infinity. You go back to your derivative now, and you take numbers on each of these intervals, and you plug those numbers in to your derivative back here. Take note of the signs that you get on the answers, and in the interest of time here, let me go ahead and cut to the results. Just understand what the process is. Taking the numbers on those intervals, plugging back into the derivative. The sign results we get back. Let me see what I got here. For the first interval, negative infinity to 0, it turns out when you plug in a negative number, you might notice that you're taking a natural log, for instance, of a negative number. You can't do that. This actually does not work. If you take a number from 0 to e squared, and e as an approximation is 2.7183, et cetera, et cetera, et cetera. So you square that out. Basically, take a number larger than 0, like 1, you plug in. If you plug in 1, you get a positive result. And down here for the last interval, something that's greater than e squared, let's be real aggressive here, 100 would definitely be larger. If you plug in 100, you would notice you get a negative result. Now what that means for the original function, wherever I see a plus sign, the original function is increasing for that interval. Wherever I see a minus sign, it's decreasing for that interval. And other things to take note of, because we talked about this on the previous problem as well, is what's going on with the derivative at these critical numbers? Well, when x is 0, what was the value of the derivative? Look at how we got 0. We got 0 from this column, right? It did not exist. As far as e squared is concerned, what was the value of the derivative? It was 0, because that came from the other side, right, where f prime equals 0. So we were supposed to find where the graph was increasing and decreasing on these. We've got those intervals defined. One last point to make that's real quick. You will see work done